So I'll be talking about extending JavaScript with Rust. And I want to start at the very beginning of the web. What are web technologies? At the beginning, it was HTML. But there's something missing. There are two very important things missing. And we realized that, and for the last 2 decades, the 3 languages of HTML, JavaScript, and CSS have been the foundation of the web. And they've evolved, and they've grown, and they've created all of the wonderful things that we can experience, as Paul said, on our phone, on a tablet, on a smartwatch, kind of everywhere. But there's still something missing. When we think about programming languages, we tend to, or at least I tend to kind of put them on a spectrum in my mind between high-level languages and low-level languages, where at the very lowest level are things like machine code, the actual raw instructions that the physical CPU inside your laptop or phone or whatever else understands. And just slightly higher level than that are languages like C and C++ and Rust, which give you complete control over how the machine code's generated, but they compile down to that native machine code. And I think control, and especially control over how memory works, is, in my mind, the key differentiator between a high-level language and a low-level language. Because with Rust or C or C++, there's no garbage collector. You can kind of choose how things are represented in memory, and you can make all these very, very deep kind of tweaks to how your program is going to run, how it's structured. Whereas at the high level, with languages like JavaScript, Python, Ruby, and others, the languages bring with them much stronger opinions about how things should work. And they typically have a garbage collector, so while your code is running, at some point, you don't have to think as a developer about, well, where am I going to get this memory for this list? And am I done with it? When do I release it? These languages free you from that, but at the cost of having garbage collection, which in most cases is great, but sometimes can give you, janky performance because your program will stop running while the garbage collector checks and frees memory, and then your program resumes running, and things like that. So it's a trade-off between not having to deal with the low-level details versus having control over the low-level details. And there are, of course, languages in the middle that let you make different choices but still kind of do the memory management for you. Does this seem like a kind of reasonable differentiation between high and low-level languages? One of the great things about developing for a native platform like Linux or Windows or Mac OS is that you can choose the right tool for the job from anywhere along the spectrum. And it's actually really common to pick both ends, to take something like JavaScript in the Node case and write most of your application in JavaScript, but rely on libraries like Node Sass that are really C++ under the hood. And they look and feel like a JavaScript library, but they're implemented in something different. Or in Python, with scientific computing, it's very common to rely on libraries that are implemented in C or Fortran so they can have higher performance and just kind of manually manage memory in those domains where it makes sense. But most of your code stays high level. And this is great until you go to the web. Because on the web, your only choice is a high-level language. And JavaScript is a great high-level language, but being a high-level language means that it has strongly held opinions about what data types are, what numbers are, how you're going to deal with memory. And if you had a problem that would be better suited by a low-level language, you don't really have the option to do that on the web. Whereas if you're using another language like TypeScript or Elm, which is also high-level, that can map very nicely to JavaScript because it has similar semantics. But if you're trying to bring something like C up to JavaScript, going upstream doesn't quite feel right. That's the missing piece. We don't have a low-level entry point into the web as a platform. Or we didn't. That's what WebAssembly tries to do. WebAssembly is kind of a virtual machine code. It's a low-level language. It only really knows about memory and numbers, and it doesn't have any opinions about how you deal with them. It's just, here's your raw stuff that you can do math with. And we can use this as a compiler target for other languages. So C and C++ and Rust can compile to WebAssembly, and then when you give that to the browser, your browser converts that to machine code and runs it. And it can do that very efficiently, very quickly, and it can do it in a way, just like when you're running untrusted JavaScript, it can generate native code that it knows is safe. So there's no risk of random files on your computer getting deleted because of some rogue WASM module, at least no more so than with a rogue JavaScript file. But what this gives us is it gives us that low-level entry point. And I've actually had this for a year. This is a screenshot of Can I Use from October 2017, when all major browsers turned on support for WebAssembly by default. We have the missing piece of the web. We have markup, we have presentation, we have high level, and we have low level. But a language like WebAssembly isn't really meant to be consumed by humans. Most low-level languages, most assembly-level languages, are really meant to be compiler targets. So the idea is that you'll write most of your code in a language like JavaScript at the high level, but then when it makes sense, when you have a problem that would be better suited by having different opinions and different trade-offs, then you can drop down to a low-level language, compile it to WebAssembly, and then use it alongside the rest of the web. We've seen a lot of this kind of compiling to the web happening in the C and C++ communities for the past 2 years in what I'd like to think of as the will it blend era of WebAssembly, where we have this powerful new tool, and we don't really know what it's good for yet, but we can kind of throw random things into it, turn it on, and see what comes out. And we're finding out that, yes, you can do really amazing demos. You can do really amazing things like putting AutoCAD in the browser, or putting a browser in the browser, or putting a browser in the browser inside WebVR. And all of this is possible on the web today, and it's amazing, but these are all kind of variations of the same trick. We've taken a big pile of native code and compiled it to the web, and now it's running in a browser, and that's fun, and it makes for good demos. But these things are really just incidentally on the web. And that's good enough if you're building video games, or you want emulators to kind of preserve our software heritage, or you're trying to bring a desktop app to the web. But there's a big difference between these things being on the web and being part of the web. And that's what I think is going to change in 2019, is we're going to move from having a tool that makes really great, marvelous demos to having a tool that is frankly kind of mundane and part of our everyday toolbox as JavaScript developers. That's what I think will happen in 2019, is we'll see WebAssembly become, we'll have good tools, we'll have a better sense of when we should be using it, and it'll just become part of our toolbox. And I think that because of some of the things that I've seen this year, the Firefox Dev Tools are just a normal web app. HTML, JavaScript, CSS, React. And we had to support, in the debugger, we had to support source maps. And that means kind of translating between this, your minified code and this compressed representation of where the tokens in the minified code map onto your original source and whatever else. And it turns out that parsing is one of the tools, or one of the classes of problems that low-level tools tend to excel at. So we took this massive pile of very, very fine-tuned, hand-optimized JavaScript, and we rewrote it in Rust, and compiled that to WebAssembly, and replaced that inside the Firefox Dev Tools, and suddenly source maps were 6 times faster. And a little more optimization, we almost doubled that to 11 times faster. And the interface is still the same, the experience is still the same, but we were able to take a task that was better suited for a low-level language, write it in a low-level language, and make our software better, and make our web experience better. We're seeing the same thing with WordPress. WordPress is working on a new post format called Gutenberg, which is how they're going to be representing data inside the database, and they needed a parser for that. They took their parser in JavaScript, and then they rewrote it in 313 lines of Rust, compiled that to WebAssembly, and got a median improvement of 98 times faster. So something like Moby Dick as a WordPress post was taking 2.5 seconds just to parse. Their Rust to WebAssembly version is taking 25 milliseconds. Again, this sort of, if you're doing something that has a hot code path that has to do a lot of data manipulation, you can now have a tool that lets you reach in and very manually and very carefully manage how you're dealing with that data, and that can yield some impressive gains. But meanwhile, the people using WordPress don't realize anything's different other than things being faster and more reliable, because the interface is still part of the web. It's still integrated into the web. We're seeing this within web frameworks as well. So at EmberConf this year, during the keynote, Yehuda Katz mentioned how within Ember, as in React or Vue or other kind of front-end frameworks, there's effectively a virtual machine implemented to kind of handle representing your DOM in memory, manipulating it, figuring out what needs to render. And virtual machines tend to be written in low-level languages, but because we only had JavaScript on the web, these have been implemented in JavaScript up until now. And so they've been working in the Ember community on replacing that with WebAssembly, and doing that by writing Rust and compiling it to WebAssembly. And what's interesting is not so much the performance gains, but what Yehuda called out as, quote, the Rust code itself looks very high level, but unlike JavaScript, that high level nature of the code doesn't come at the cost of unpredictable performance. Because when you're doing manipulation of data, when you're doing parsing, when you're doing this low level work, being able to opt out of garbage collection gives you much more reliable performance, because your program won't stop running and let the GC sweep and then resume. And so the view within the Ember community was, hey, we can take these critical core hot paths of our code write them in a language that still feels high level, and now we can get more reliable performance. The higher levels stay in JavaScript because it makes sense to keep business logic, high-level logic in JavaScript, but the low-level things can go to a low-level language. That's WebAssembly. The common feature of these examples is that we've had existing projects take a module, rewrite it in Rust, compile it to WebAssembly, and see amazing gains. And I think that's because Rust not only is a really incredible language, it has the benefits of a high-level language, the feel of a high-level language, but it works like a low-level language. But Rust has also invested a lot of time and effort into trying to build the best tooling for targeting WebAssembly of any language. And so what I'm going to do is I'm going to do a little demo where we'll work through this. But what I want to do is emphasize the idea of modules. In the JavaScript community, we've adopted modules. We've kind of come around to this idea that, yeah, we should have, here's the code. It can export functions. It can import functions. The future we want to work to is somewhere where your JavaScript can rely on a WebAssembly module, can rely on JavaScript, and it's all just kind of the same. It's all an interface, and you don't have to care or see what's inside each module. You have a function, you call it, you get a result, done. So let's do an example. There's a code challenge called Advent of Code that runs every December, and it gives you a daily programming puzzle. And I really enjoy them. They're clever, they're fun, and they're a great way to play with new programming languages or new concepts. So the first part of the puzzle for the first day last year had the question, given a string of digits, sum all digits which are followed by the same digit, and then consider that the last digit is also followed by the first again, so kind of like it loops around. And we're going to solve this in Rust and compile that to WebAssembly and see how all of this works kind of end to end. What this problem is saying is more or less, if you have a number or string of numbers like 1, 1, 2, 2, well, the 1 follows 1, the 2 follows 2, so we add those together and the result is 3. Or with 9, 1, 2, 9, well, it wraps around, so we count the 9, and that's our sum. 1, 1, 1, 1, everything follows everything. 4, 1, 2, 3, 4, 0. So it's simple, but it's kind of a fun challenge. I'd encourage you to try write this in JavaScript and kind of see what that looks like compared to what we get in Rust. One of the nice things about Rust having the semantics of a high-level language is that I can start writing solutions, and I have this great support for things like iterators and these other high-level concepts. So I'm going to build this in kind of a functional way using iterators, where I'm going to set up an iterator called current and one called next. I'm going to make the next one an infinite loop, and I'm going to advance it by 1. And now what we can do is if we zip these together and kind of advance them in lockstep, we can see which number is each iterator pointing to. If they're the same, add it to the sum. If not, skip it and keep going. So at first, we have 1 and 1. So we add a 1. Our sum is 1. Done. Next, we have 1 and 2. Nothing changes. Next, we have 2 and 2. We add that. Sum is 3. The next iterator loops around to the front. The current iterator is done. Nothing happens. We can't go any further because we're out of items in one of the iterators. That's our result. So this is how we're going to solve this. And when you think about languages that are a low level, you tend to think about things like C and C++, where you don't have the same high-level facilities that I'm about to show you. This is all standard Rust. So we're going to start with a function called solve that takes a string as input and returns a number. We'll create our 2 iterators. So input.chars gives us an iterator over characters. We'll make the second one infinite, and then we'll skip it ahead by 1. So this is all it took in Rust to get to this initial state, where we're ready to start iterating in lockstep and summing up our result. Rust is a strongly statically typed language, just like TypeScript. So you get the same benefits, but you don't have to write out the types necessarily, unless there's an ambiguous case, and inside the function signatures. So you'll see that input is a string, the result is a 32-bit integer, but I don't have to write out types anywhere else. What I want to do is I want to zip those 2 iterators together, so I get a single iterator that gives me 1 item from each at a time. So current.zipNext. Then I'll call filter map on that and say, all right, for every x and y, so for every item from current and every item from next, if x equals y, then x to digit. So this is just like parseInt. I'm going to turn that from a string, from a character, into a number. Otherwise, nothing. Filter it out. That's the core of our logic in Rust. And to sum this all together, we can just call .sum. And this is part of the standard library. Rust has these great data manipulation tools built in. That's all it took to solve that problem. So now we need to put this into something that we can use in the web. And we're going to use a tool called Wasmpack to do that. The idea behind Wasmpack is that you write a library in Rust, and you compile it to WebAssembly. But remember how I said that WebAssembly only understands numbers in memory? WebAssembly doesn't know what a string is. And Rust's idea of a string might be different than C or C++'s idea of a string. And so what you need to do is you need to have some sort of layer in between the two that says, all right, here comes a JavaScript string. Let me convert that to something that you'll understand on the other side, put it in memory, and then kind of tell Rust where to find that in memory to deserialize it. Wasmpack will generate that binding for you. Wasmpack kind of does all the heavy lifting of saying, all right, here's your Rust code, here's a JavaScript wrapper around it, and by the way, I've also created a package JSON and a README for you, and it could be npm installed. At which point, you can just toss it up onto the npm registry, and we're moving towards this world where you npm install something, and again, it may just be a JavaScript module, but it may have JavaScript, it may have WebAssembly, and you don't know and you don't have to know. Your experience as a web developer, as a JavaScript developer, stays the same. It's just that the underpinnings, the libraries you're relying on might be implemented in something different. Let's try to do a little bit of that live. So here's my code, the same JavaScript I showed you, or same Rust I showed you earlier. And Rust has great testing support, so I can actually, inside Visual Studio Code, just click Run the test, and hey, my test works. So my code is OK. And if I want to build this, let's see, I can run Wasmpack build. Oh, hey, wait, I don't have WASM bindgen as a dependency. So Wasmpack will actually walk me through the things I need to modify inside my Rust library to make it compatible with WebAssembly. The first thing it's telling me to do is that I need to depend on a new kind of third-party module called WASM bindgen. I'll save that. And then I also need to annotate which functions I want to export. So I'll call WASM bindgen on top of that function, and then I need to actually bring these WASM bindgen things into the namespace. So I'll use WASM bindgen prelude star. So new third-party dependency, 2 lines inside this Rust file, and now when I Wasmpack build, I wonder why that's wanting me to recompile. Well, this may take a second. I thought I had pre-built this so it would be fast, but the idea is that this will spit out in this package folder a TypeScript definition, the JavaScript bindings, my WebAssembly file, and my package JSON. And so I have an npm module that happens to wrap up this WebAssembly Rust library. And this isn't super exciting. This is supposed to be really mundane because we want this to be a tool that you can use in your day-to-day work. So you run into an issue where you're like, man, I really wish I could handle exactly how this matrix is stored in memory. Well, all right, yeah, go do that. Rewrite that function, compile it, Wasmpack it up, and you're good to go. So over here inside, I've got a normal web. Well, actually, that reminds me. So one of the cool things, static typing. So I can, in Visual Studio Code, hover over any of these things and see, like, all right, chars gives me a chars object, cycle, whatever. I can see all this wonderful typed information, all these documentations. Very nice. If I go to my web project, where I just have kind of a normal WebAssembly module, I've got an index file that has 2 inputs, an input and a result, and I've got a JavaScript version of the solution to that problem, that puzzle. So inside Webpack, I can say, all right, my index.js, import star as advent from advent.js, find my input elements, and then add an event listener. So whenever I type something, I'm going to change the result value to advent.solve and pass it the input string, right? If I go say npm run start up the Webpack dev server. So this is using a JavaScript version of that solution. Refresh this. I can say 1, 1, 2, 2. Result is 3. 9, 1, 2, 9. It works. All I have to do to switch out the JavaScript module for the WebAssembly module, let's go ahead and delete this, is in my package JSON, I need to depend on my kind of compiled Wasmpack file. So I'm going to say, all right, my dependency advent is on the file system. I didn't want to use the internet and actually go out to the npm registry, but it's at advent package. Save that, and inside my index.js, well, instead of importing from advent.js, let's just import from the module advent. All of my JavaScript code stayed the same in my application, but now this logic has been replaced with the npm dev server, or Webpack dev server, replaced with an implementation in WebAssembly. Refresh. Same result. It's utterly mundane, and it's one little module, one little function replaced with an equivalent functionality written in another language. And that's as it should be, because this is what brings the ability to us as JavaScript developers to finally choose between a high-level language and a low-level language, or choose alternate tools when something might be better suited to a given problem. And that's kind of it. That's the workflow we want to enable. And right now there's a little bit of boilerplate that you need, but we have documentation, we're working on that. You can find an introduction to Rust at rust-lang.org, and then you can find docs on Wasmpack at github.com/rustwasm/wasmpack, wasm-pack. And that's all there is to it. So you today, as someone in the JS world, can sit down and pick up a language like Rust. It's not scary. It looks and feels like a high-level language. And when you have something, when you're profiling your code and you're like, man, this particular function or this particular part of my code is being run a lot and it's taking a lot of time, well, hey, maybe now you can actually fix that. That's what I wanted to show you. We're moving from the will it blend era of flashy demos, from the idea of kind of things that are marvelous to things that are mundane. But I think that's important, because what I want to see us do, what I want to see happen, 3-4 years from now, is that you walk into something like RuhrJS, and the presumption is that, of course, we're relying on not just JavaScript, but JavaScript and all these other supporting tools. Just like today, we think about JavaScript and CSS and HTML as part of the web, I want you to think about WebAssembly as a part of the web. Thank you so much. If you have questions, I'll be around all day.